All right, so the first example, the square wave. All right, basically what it all comes down to is creating this alpha n that I have here, right? So we go into that formula. What is the very first thing I can do? There's a critical step I got to do to figure out how to get that alpha n. What's the very first thing I got to do? Figure out what my period is, okay? And then figure out what. Once I know a period, I got to figure out what. It's really
X of t.
X of t. I got to figure out a function for X of t over that period. So the way I did this before is I said the period I'm going to consider is going to be from this guy right here, 0 to t. And I think in my example, I used t equal to, what did I use? Well, I used actually t equal to 0.001 seconds in my code. Okay, that's my period. But I kept this in terms of capital T. So I got to get a function over that period. So what I did here was I wrote out my X of t. I said my X of t is 2 in this case, from 0 to t over 2, and then it's 0. That led me to say, okay, well then here's how I evaluate the integral. Now, one of the things about this process is when I went through this, I went through it and I basically did the integration. So e to the at is what I have here. So one of the things that I saw people suggesting in Discord, which I would recommend you to do too, the equations in MATLAB can get pretty ugly pretty fast, okay? If you're writing those all out on one line. So you have something like j n omega naught, do like what I'm doing here. I'm saying that's the same as a, right, e to the at. So write that out as a equals negative j n omega naught, like that, right? I can make that definition in my MATLAB code and make my MATLAB code a hell of a lot more readable. All right, if you just try to write this stuff in there, it's going to get pretty ugly pretty fast. My suggestion is defining some intermediate variables like that, particularly for problem 2. Problem 2, you got a bunch of integrals to do, right? So in this case, in that case, you probably want to break up your equations into multiple different pieces and string them together, right? So my other suggestion is when on Monday last week, I derived this, went through it, it's recorded, the notes are there. I didn't take it any further than this, okay? I said the example that folks were looking at in the book, they basically went in and said, well, e to the j, or negative j n pi in this particular case, they used Euler's identity and said, well, that's cosine n pi minus j sine n pi, like that, and then simplified that further. That, you could do that. There's nothing wrong with that, all right? But I'm not asking you to go that much further, all right? That's not a, it's illuminating, I guess, to some extent, because I can see that certain harmonics disappear more clearly than I can from that first one. But that's not the question I'm asking you to solve, right? If you can do the calculus to get yourself to here, that makes me happy. All right. I don't need you to do the parlor tricks to get it any further than that. All right. If you want to, you can. All right, but don't think that you have to. All right. Now, let's talk about coding this. Back to my problem, right? So please determine a formula for the okay, we did that. We determined the formula for the complex Fourier series coefficients. Include a vector that contains all the coefficients from n equal minus 100 to 100, okay? And then I ask you to do it for the C's, the thetas, the A's, and the B's, okay? So I've said I want alpha n, I want an, I want bn, and I want cn, and I want theta n. All right, and I've said that harmonics that I want 100 harmonics, okay? One thing you want to ask yourself is, how long are each of these vectors going to be? How many entries am I going to have in my alpha, my A, B, C, and theta?
201.
201, yeah, 201 for this, okay? Where'd the 201 come from? Well, because in the alpha form of the series, right, I go from n equal negative 100. So Yeah, let me write the full alpha form of the series is this. Okay, so x of t is equal to this. So the n corresponds to the harmonic numbers, right? So in the alpha form of the series, if I want to have that, I always have a positive frequency and a negative frequency. So this becomes 201. Why not 200? Where'd the extra 1 come from? The DC term, right? The DC term doesn't get a reflection, right? There's only 1 0 there's no negative 0, right? What about A, B, C, and theta? What's going to be the length of those vectors? 101. These guys are each 101 entries because I'm telling you for 100 harmonics, right? And why 101? Because I start at 0. Okay. If I think about it, if I told you to do up to the first harmonic, I'm going to have DC and 1. So it's always going to be 1 more than the number of harmonics that I'm asking you for. Okay. So thinking about that, why is my t vector, I saw somebody say, well, the length of that's 20,001, right? Why is my t vector so much longer than all the other ones? Why does the t vector get to be longer? What am I doing in the code? Well, back to the question, right? Ultimately, what I end up asking you to do is I tell you to plot the Fourier series coefficients, or to plot your Fourier series using the complex form of the series. If this is not clear, when I say plot your Fourier series, that means I'm asking you to plot x of t, right? So you should be plotting alpha 0 plus alpha 1 e to the j omega naught t plus alpha minus 1 e to the negative j omega naught t. And you're doing this all the way out to the 100th harmonic. So how big does your t vector need to be? Well, it needs to be a heck of a lot bigger than alpha does, right? Why? How do I size a t vector? How do I typically size a t vector? Yeah, so I can see it. I'm telling you to see 2 periods, right? I think I tell you to go from negative t to t, right? That's going to show me 2 periods, negative t to 0 and 0 to t. And so the step I tell you to use is t over 10,000. Now, why? So normally I do like t over 100. All right. Any idea why I chose t over 1,000 or t over 10,000? Why so much smaller? Why so much smaller here? No idea. Well, yeah, I mean, so my graph has finer steps, right? Certainly, if I use a finer time step, which is what I'm doing, right?
So when you get to the 99 harmonic, the changes in the waves are so small.
Yes. Yeah, you picked up on this, right? So what is, if I asked you if I see you on the street in 10 years and I ask you how to compute the alpha n, none of you be like, what the heck are you talking about? Right. But if I ask you what is a Fourier series, I hope you would know what is a Fourier series. It says that if I have a periodic waveform, I can add up a bunch of harmonically related sinusoids to sort of create that waveform. So what I'm doing is you're adding up sine waves that have harmonically related frequencies. So by the time I get to the 100th harmonic, I'm adding in cosine 100 times 2 pi, in this case, whatever 2 pi over t, I guess I'll put it that way, plus theta of 100, right? What's the period of that guy? It's 100 times smaller than it was at the fundamental, right? So I'm choosing a smaller time step to make sure that I can capture up to 100th harmonic pretty well, and it doesn't end up screwed up, right? That's why I didn't make you think about that at all. I said, oh, just make it this. Okay, here's the T vector I want you to use, right? So I didn't make you think about that, but you should recognize if you look at this, right, that the fundamental frequency, yeah, that has, for that I would only need T over 100. But if I'm asking you to plot, and I am, and that's the thing you may not realize, I'm asking you to plot stuff in here, sine waves that have 100 times that frequency, in which case I'm going to need a much smaller time step to make that look right. Okay, that's why that it has the step that it does. The thing then, so those vectors should be very different sizes. Okay, so again, the code from last week that's there walks you through pretty much how to do this, right? So if I go back to the question, right, the question basically was, all right, you get a formula, all right, plot the Fourier series using the complex form of the series, set up your time vector, and then fill in your alpha vector. So if you look at what I did here, I have a for loop for loading up my alpha vector right here. And what I did was I said in this particular example, right, I just said I let n equal to 2. So that's going to give me 2 harmonics, right? I loaded up my alpha vector by basically just appending the next value to my alpha. So what I talked about last time is I said alpha n is equal to square bracket alpha n and then the next value. Now, some of you guys may say, well, I don't like that. It looks messy, right? That does get messy pretty fast. So one thing you could do, which would make this nice, a little bit more visible, if I could take this out right here and do something like this. I could say value equals that. Okay. So if you look at what I just did right here is I basically just created some intermediate variable, right, that said val, I called it, is that formula, and then I appended this on here. It makes it look a heck of a lot cleaner if you create those intermediate variables like that. It probably makes it easier for you to follow. When you put it all on one line, it gets super messy, super fast, especially with all the parentheses and all that kind of stuff. Okay. Now, what I did then was I basically, this is the critical next loop. There's 2 loops that are really critical. The first loop is where I created the alpha vectors. The second loop is right here, where what I did was I wrote a for loop to create this sum. Okay. And what am I doing? I'm looping through the n vector. I created this vector I called n complex. N complex went from the negative harmonic I wanted to make to the positive harmonic I wanted to make. I looped through that. And what I'm doing is I'm basically trying to implement this summation right here. Okay. So what I'm doing is I'm saying so f of t is equal to this. That means that if you think about what this loop's going to do, I'll write it up here, right? F of t, or I'll do it as x, since I wrote it as x of t here. X of t is equal to n equal to negative infinity to infinity alpha n e to the j n omega naught t. What I'm asking you to do, because you can't do it from negative infinity to positive infinity, is I'm asking you to do it from negative 100 to 100. Okay. So what I do is I created a vector n, which starts at negative 100, increments in steps of 1, and goes to 100. Right? That's gonna be the n vector I need, and I already have an alpha n vector. My alpha n vector starts at alpha minus 100, whatever value that is, and increments all the way up to alpha 100. Right? If I looked at what's in that vector, I would see that alpha minus 99, so on and so forth, all the way up to alpha 100. Okay, so those 2 things would be the same length. Okay, so if you think about what my for loop would do, the first for loop I wrote, this guy, I loop through basically through the length of n complex. For each time I run through this, I calculate one number. Because what I'm doing is I'm calculating the value of alpha n for that value of n. My second for loop, how many calculations am I going to do? The one where I'm filling up this vector right here, where I'm filling up x, how many calculations do I have to do there? 20,000. Yeah, because I'm basically filling up the x of t vector. So when I look at it, when n equals, and actually the way I did it, this is a tricky thing to loop through, right? Because I don't say for n equal to 1, right? I'm going to loop through this thing. So what I did was I said for k equal 1 in steps of 1 up to, I would say, the length of n, right? I'm looping through that vector, and I'm basically trying to implement this summation as a for loop. Okay, so what's going to happen the first time I go into that for loop? I'm going to create an x. And what's that x going to be the first time I'm in that for loop? What would I write out for it? Yeah, you basically, every time I go through that for loop, it's calculating alpha n e to the j n omega naught t. Right? Every time I go through the loop, I'm doing that, and I'm adding it to whatever I had before. Right? So that's why what I'm saying is I can think of this as being whatever x of t is right now, right? So whatever I currently have for x of t plus the thing I have for the next vector, right? Or for the next value of n, right? So the very first time through, if you think about the way this guy's going to expand, there's going to be a value for negative 100, for n equal to negative 100. Then you're going to add on a value for n equal to negative 99. And then I'm going to add in values for negative 98. So what I'm doing here is I'm saying, all right, x is equal to whatever x already is, plus whatever this is. Well, how do I code that in? I say it's alpha n of what? Whatever k is. K is my index through the n vector, right? And then I multiply that by exponential j times n of k times t. The fact that I'm multiplying by t is going to make this guy a vector of time. And I'm basically just walking through it that way, right? So every time I go through this, I'm going to go through it, in this case, 201 times. Okay. And every time I go through it, I'm going to add on to a vector that's 20,001 long, another 20,001 entries. What's that? Oh yeah, and there's an omega up here. Yeah. Times omega naught. Times t. I'm out of space there. Okay. Somebody gonna ask a question online there?
Oh yeah, I have a question. I think my confusion was whenever I was solving it mathematically, the form that I got for my alpha n coefficients didn't really reconcile with the code. So should our alpha n coefficients typically have the same form, or is that dependent on the function?
What do you mean by the same form?
So like 1 over j n pi, 1 minus e to the negative j n pi.
No, your alpha n's should be whatever your alpha n's need to be based on the function.
Okay.
So in this case, the example I had open my PDF here, the book. This, I think one of you might have been the one, Anthony, that pointed this out, right? So this is actually, if you look at, this is not exactly the same, but pretty darn similar to the one that I have for you in problem. In fact, it's really similar to the one I have in problem 1. All right. If you look at this, so again, so they did this from negative t over 2 to t over 2. What I was saying is this formula is similar, but not exactly the same as what mine is, right? This is about as far as I would have gotten in simplifying it. What did they do here? They basically made some substitutions using Euler's identity. saying e to the j theta is equal to cosine theta plus j sine theta and simplified it further. You can do that if you want to, but as long as you got something like this, then you're close enough. Does that make sense, Anthony?
Yeah, definitely. Appreciate that.
Okay. All right. Any other questions about what I did to develop this code here? All right. Now, the other thing I did is and I had this in there before, but I threw this back in there today. And when I ask you to calculate the A's and the B's, what did I do? Well, I just used those formulas that I've given you guys before for calculating, so if you look at this, the C's, basically that's the magnitude of the alphas times 2, right? If I look at the thetas, it's the angle of alpha, all right? If I look at the A values, it's C times cosine theta. If I look at B, it's negative C times sine theta, right? So I basically just followed along with those same formula sheets, right? And I had it ready to go. So here's the actual MATLAB that I created in MATLAB. Right. So I take that function. In this case, I've got n equal to 10. All right. And I can just keep changing it however I want. Right? I run that. And I get that. Okay. And I can change the number of harmonics, and it's just going to get closer and closer to the real waveform. Right. So let's say I chose n equal to 100, which is sort of what I've asked you guys to do. If I do n equal to 100 for the square wave, I end up with that, right? So it got even closer to the original square wave, right? That's basically what you're doing. So you should see for problem 1 that it looks kind of like whatever that triangle waveform is by the time you're done. And I think in problem 2, the approximation should look really good. It should look much better actually than it does. You don't get the ears, I don't think, in that one in the same way. All right. Now, let's look at this example. Let's say I want to do the same thing for this. All right. Where do you start with this one? Because I think part of the problem you guys may have is in calculating the alpha ends. So where do I start to calculate the alpha ends for this? Well, I go to that formula, 1 over t. Again, I can go, so from little t to little t plus capital T, x of t, e to the negative j n omega naught t dt. So where do I start with the one like this? Okay, so what's my period here? 2. All right, I wouldn't use that. I would just set up a variable. It probably says t equals 2. I'd do my integral in terms of t, most likely. All right, what period would I integrate over? You can choose whatever period you want, right? What period you want to do it over? 0 to t. All right, that's one option. I could have done negative t to 0, right? All right, so let's say I did it 0 to t. All right, once we've determined that we're going to do it 0 to t, that means I'm doing it from here to here. So what's my next step? And this is the critical step. I have to define x of t. So what is x of t? There's 2 pieces over that period. What's the first piece? 0. 0 for 0 to t over 2 in this case, right? Which is 1 second. What is it for the next part of the period? It's linear. So what do I have to do?
Find the equation.
Yeah, I got to find the equation for it, right? So and how would I do that? Well, it's the equation of a line. So I got to figure out, what's the, it should be of the form, x of t equals mt plus b, right? So I got to figure out the slope. I got to figure out the y-intercept. What's the slope of that guy? So the maximum value here is 2. right? It starts to rise at 1, stops rising at 2. So what's the slope of that? 2, right? The slope of that's 2. What's the y-intercept? That you would have to figure out would, yeah, if you would have to do the math to figure out that that guy's -2. How would you do that if you didn't know? Well, one thing I would say is x of 0. Well, let me say it this way: x of 1. If I said x of 1, right? So I plug in here 1. What's x of 1 equal to according to that picture? 0. So I solve for b. So if I think about it, right, b has to be equal to -2. So I've got a function there. So that means that this guy becomes the integral of 1 over t from, let's see, let me write this here. So this becomes 2t minus 2 for the second half of the period, less than t, like that. So this guy would be from t over 2 to t of 2t minus 2 times e to the negative j and omega naught t dt. That's my integral now. Right? What does that mean I got to do with that integral? It's not a very fun integral, right? Why not? What's the problem with this guy? I got to do integration by parts. And you're going to have to do that on problem 1 and on problem 2. And on problem 2, what sucks is you got to do integration by parts how many times? Twice, right? There's 2 different pieces where you have to do it, right? So problem 2 is a shade on the lengthy side, yes, right? Because of that. But if you look at this, if you can follow the process here, right? Now this, when you look at something like problem 2, I don't remember exactly what it looks like, but it's something like this, right? It's, isn't it? Something like that, sort of trapezoid shape or something. It's a trapezoid, isn't it? Yeah, I think so. So when I look at that, how many portions? So I say you got a portion here, you got a portion here, you got a portion here. So you got 3 integrals you're gonna have to do, right? Is what it comes down to. Now, you got 3 integrals you're gonna do. That means you can get 3 ugly formulas, right? So what I did in my code, just so you're aware of that. So what I did was, in the same way that what I wrote up here. So notice these thing I wrote where I said value equals this. And then I said I appended to alpha n that variable. If you do this guy, you're going to get 3 integrals, right? So what I did was I said, well, val 1 is the result of this integral. And I said val 2 is the result of this integral. And I said val 3 is the result of this integral. And I just wrote out a separate formula for each one. Each one of those is a formula in terms of n. Right. And what I did was I said val equals val 1 plus val 2 plus val 3. Right. I defined that line in my code. And then I said, when I filled in my alpha n vector. In other words, let me tell you this. If you get code that works for problem 1, it's pretty easy to get code that works for problem 2. You can literally copy and paste it. The only thing you got to do is just change your alpha n formula. That's it, right? There's no reason to start from scratch a second time, right? So what I say is my alpha n is alpha n, and then I said val like that. And I just appended it and I looped it through, right? And then each of these lines of code would be in terms of my n values. Okay. If you try to write out in one line of code in MATLAB what that formula is going to look like, especially in that little window, you're not going to follow it. You're going to lose your brain pretty fast. Okay, because it's going to be very ugly what that formula looks like. All right, so writing it out sort of stepwise like that is a really good way to try to do it. All right. Questions? All right. I know you'll ask questions once you do it, but that process, was your questions on there? Comment?
So you had some like code that you wrote out, just like, oh, you actually wrote it out earlier, just a second ago. And you had like the whole expression, exp times j times n times that's t.
Yeah,
Would you need to index t in that situation?
that's a great question. I could, but so the for loop that I am doing, okay. The for loop that I'm doing here, I'm not looping through t. Because what am I doing? I'm looping through my, so each time, if you think about, so you really have to think about this formula right here, right? If you think about what this formula f of t equals to that summation, I'm looping through because of the summation term. And I'm basically, every time I go through it, my t vector is the same size. I'm plotting it over the same time frame, right? But I'm adding another harmonic in. So I'm adding another value of n in, right? I could, if I wanted to, also, I could have a nested loop and I could loop through my t vector and calculate each individual point, but that would be ugly to do. But you could do that. There's just no need to. Yep. All right. All right. So moving on, I want to pick up with what I started talking about at the end last time. Okay. Which is this idea of where do I kind of apply this? Well, I apply this in the context of filtering. All right, so the example I started to give is I said, okay, well, a common thing to do is to say, okay, I want to drive a DC motor, let's say, in a robotic application. I want to drive a DC motor, and what I have is, microcontroller is what I can drive this with. So I got a microcontroller and a motor drive, and the microcontroller generates a square wave that looks like this. And this guy is 12 volts, right? And I said last time, if this thing is what I call pulse width modulation, I change what I call the duty ratio, the percent of time that this thing is high. Then I called this here, this is the voltage I apply to the motor. And that means that this voltage I apply to the motor is equal to some kind of a summation alpha n e to the j n omega naught t. All right, like that. So I go through, basically what I'm saying here is I can think of this thing as a sum of sine waves. Now, this is a DC motor. A DC motor, basically, to make a DC motor spin, what kind of voltage should I give to a DC motor, do you think? AC or DC? DC, right? But I'm giving it AC, right? So what ends up happening is this motor only responds somehow to the DC component of the voltage. So somehow there is a relationship between the voltage I apply at the terminals here and the speed that I get out of the shaft. And there's a relationship that comes from a differential equation, but there is also what I call sort of an impedance-like relationship that I can figure out. And that's what we're going to try to work out today. What is that? There we go. That was weird. So what I have in the case of a motor, right, is more generally, I don't have a circuit now. I have a system of some sort. What I have is I've got a voltage source, which is an ugly looking voltage source. It's this guy that I am applying somehow to a motor. All right. And the circuit model for a motor is a complicated thing, right? I'm not going to get into deriving it or whatever, but it's going to be some differential equation. Basically, what that differential equation is going to look like is sometimes I refer to the speed of the motor as omega, capital omega here. It's a very common way to refer to it. Okay. In physics, you probably heard of rotational speed in that context, right? So what there's going to be is there's going to be this relationship for the motor, which will look like this. there's some differential equation relationship that's going to exist between the motor speed and the voltage I apply to the motor. Right? And again, not going to get into to walking through that, but there's going to be some differential equation thing that's going to develop for it. So what I'm going to end up with is the differential equation between an input and an output. Okay, so let's just look at this here real quick. So let's say I have this sort of a relationship. I have kind of a process for how I would use the Fourier transform to allow me to approach this type of a problem. Okay, so if I have a cosine, a cosine omega t plus phi, I want to think of this, all right, as in a way that I can relate to the Fourier transform. So we know we've learned, multiple different ways to represent a cosine. If I give you a cosine omega t plus phi, how can I use Euler's identity to put that as two rotating vectors? What would be the relationship? A cosine omega t plus phi. How would I write that in terms of the two rotating vectors? What would that
It would be
be?
the a over 2 and then e to the w t plus e to j phi and then the negative version, which is just, yeah.
Yep. Yeah. So usually I write the a e to the j phi first, right? But yeah, she's exactly right. That's my positive rotator, and then I have my negative rotating term, which is this. Okay. So that is how I put it in that context. And what I've said is, in looking at it, so if I had this as my waveform, if this was my, in this case, this is my Vs of t that I've written here. What I have is that Vs of omega, the Fourier transform. That's what we went through last time. The Fourier transform of this thing is a set of impulses, right? It tells me the places where I have information. So somebody tell me how would I set this guy up? And I guess let's get a little bit confusing. Let me call this omega naught. All right. And if you want to think of it, let's say omega naught has a number. All right, let's say it's 1. Okay. How would I write Vs of omega? How did I write that? How do I end up writing that? Yep, that's where I basically said this thing is where I've got those impulses, right? This guy goes from omega equals to, well, we did this in terms of n equals minus infinity to infinity, alpha n delta of omega minus n omega naught, like that. Okay. So in this case, this guy's going to have, first of all, how many terms is this going to have for this waveform? How many terms will this have?
2.
2, right? This guy's going to have a over 2 e to the j phi delta of omega minus omega naught. That's for this term. And then it's going to have plus a over 2 e to the negative j phi for delta of omega plus omega naught. Okay, so he's got 2 impulses that appear. Okay, and we talked about how to graph those, and we're going to look at another example of how to graph those again. You have that in problems 4 and 5 and 6 in the homework, right? So, all right, I've got that. Then what? Well, what I want to do is I want to say, how can I, if this is my input in general, how does that relate to this differential equation? Well, so if my input was of this form right here, my input is of that form. Why is it doing that? Yeah, my input is of that form. So Vs of t is, I'll write it this way, alpha 1 e to the j omega t plus alpha minus 1 e to the negative j omega t. All right, and I'll keep it in terms of omega naught like that. Okay, so if that's my input, when we did differential equations, what happens when we put this in here? What should my solution form look like? And let's just do the positive rotating term here for a second, right? Let's just do the alpha piece. If that was my input, because I don't have to look at both of these together, right? If I think about this, if I have a differential equation, I have two inputs. That's superposition. I don't need to look at both of them at the same time. I can look at them separately. So if I had alpha Vs of t is equal to alpha 1 e to the j omega naught t, like that, what would my v of t, so in this case, Vs of t is my input, v of t is my output. What would v of t look like? It would be an exponential with the exact same frequency, right? So what I would say is that this guy is magnitude b, e to the j angle b, e to the j omega naught t, like that. I know that's going to be my output. Okay. So we know that if I have an input of a particular form, my output has the same form, right? That's always the case. If I put a sine wave in, sine wave out, exponential in, exponential out, constant in, constant out. The values may be different of those constants and everything, but it's the same. The input and output always have the same form. So if I went and I what do? I plug that into this equation, into this differential equation. All right, so I kept this super general, right? So I have k derivatives. Let's keep it simple. Let's say it was just a first order, a1 dv dt plus a0 v of t equals Vs of t. All right. Well, what do I have to do? I got to plug in Vs and V, right? My guesses. Right. So if I think about that, and I'm going to call this, I said, so B e to the j angle B. I'm going to write that just as B e to the j omega naught t. And I'm going to write off here to the side, B equals magnitude of B e to the j angle B, like that. Okay. So I plug that in, what happens? What's going to happen when I do that? What's going to happen to the e to the j omega naught t's? They're all
They
going to
can't-
cancel. Yeah, they cancel, right? So I get over here alpha 1 e to the j omega naught t. And then on this side, I have a1 times b, the derivative of my guess. So this, what's the derivative of this thing? So j omega naught comes down, and then it gets multiplied by e to the j omega naught t. And then this guy is just b e to the j omega naught t. So if I look at that thing, every term has an e to the j omega naught t. So that's been removed from the equation. If I solve here, so again, the thing I'm trying to figure out is what b is. I want to know what the magnitude of b is, and I want to know what its angle is. So I'm trying to solve for it. So if I look at this guy can be rewritten now as b times j omega naught a1 plus a0 equals alpha 1, like that. Okay. So specifically in looking at this now, if I want to solve for b, I see that b equals whatever alpha 1 was divided by j omega naught a1 plus a0. That's what I ended up with. Now that if I look at the relationship that I have here, this guy is the angle and magnitude of the output at the frequency omega naught. This guy is the magnitude and angle of the input at the frequency omega naught. What I'm basically finding here is don't know why it keeps doing that. What I'm finding here is that this magnitude at the output is related to, so this is, let's capture it this way. This is the magnitude. Let me not call it that. Let me call it the phasor. This is the phasor for the output at omega naught. This is the phasor for the input at omega naught. And what I have here is this relationship alpha 1 times 1 over j omega naught a1 plus a0. This thing right here is something that I call a transfer function. It tells me, and it specifically, this tells me the value that the system applies to the input to get to the output. Okay. And in particular, what I see is if I have a differential equation of this form here, if I have a differential equation of this form, let me pull it down here. So something of that form, I don't have room for it here. If I have a differential equation of that form, then what I end up getting is that why is it doing that? It's weird. Okay. These alpha values are the coefficients of the Fourier transform. The values of the Fourier transform at particular frequencies. And these are the coefficients of the Fourier transforms at the output frequencies. All right. So what I end up getting from this whole process is that in general, the Fourier transform of an output, okay. So I guess is the way, in terms of the way I've written this here, I guess I'll say B of omega is equal to, I want to stay consistent with the relationships here. So my output is V of t, my input is Vs of t, okay? So just to be clear on this, what's it doing that? So if Vs of t is my input and V of t is my output, this guy has a Fourier transform Vs of omega. This guy has an output V of omega. What I have is this relationship here that says the output Fourier transform is related to the input Fourier transform times this thing H of omega, okay? And what I'm doing is if I want to know basically the phasor at a given frequency, I need to know the phasor at the input frequency and what this transfer function is at that frequency. So in the context of this sort of generalized form here of this differential equation, what I can say is that this H of omega thing will always look like this. It'll always look like 1 over again, I'm going to keep it consistent with this form of the differential equation here. It's always going to look like this. A1 is equal to j omega for the kth derivative plus j omega to the k minus 1 derivative times a k minus 1 all the way down to j omega times a1 plus a0, like that. That is this relationship. So in other words, this guy here is a transfer function. That is an impedance, right? If you sat and you had a circuit that looked like this particular circuit, and I said I had V in of t, and I wanted to figure out what V out of t looked like, what you would do is if I asked you that question, you would write the impedance, right? So when you do impedance, I talked about this very briefly at the beginning of class the other day. If I say do this using impedance, then I don't have V in of t and V out of t anymore. What do I really have? Yep, I have their Fourier transforms. I have V of omega like that and V out of omega. And what I have is a transfer function that relates those. So so I could look at a differential equation here. So let's not do a differential equation. Let's do this first in terms of how would you do this in terms of impedance? If I said to you, figure out V out of omega in terms of V in of omega, how would you get that? How would you write that? You could do KVL. Hopefully you recognize this is a voltage divider. Right? If this is a voltage divider, how would I write out V out of omega?
It would be the impedance of the capacitor over the resistor plus the impedance of the capacitor.
Yeah. So it'd be 1 over J omega RC over 1 over J omega RC plus, well, I'm simplifying it further. The impedance of the capacitor, 1 over J omega C over 1 over J omega C plus R times V in of omega. Now that we don't usually keep it in that form. We usually end up simplifying that down. So it's what I call a rational function. So if I multiply top and bottom here by, so normally what I would do is I'd multiply top and bottom by J omega C. If I multiply top and bottom by J omega C, that means I'm multiplying by 1, right? If I multiply top and bottom by J omega C, what happens to that expression? What happens to the top? 1 over J omega C times J omega C is what? 1. On the downstairs here, what happens? 1 plus J omega RC, right? Plus 1, right? Times V in of omega. Like that. So V out of omega, the phasor for the output is equal to the phasor of the input times 1 over J omega RC. Now, I should be able to relate that to the differential equation based on the analysis I just did. Okay. So again, let's just try to do that. If I wrote the differential equation, I would say V in of t is equal to what? Somebody help me write the differential equation for this. The voltage across the resistor plus the voltage across the capacitor. So what's the voltage across the capacitor? Well, I've called that V out. How do I do the voltage across the resistor? What would that be here?
I times R.
Yeah, I times R. So what's I?
Current.
It's current. What's the current in terms of, if I want to get a differential equation here, what's the current?
I is equal to C times dV dt.
I is C dV dt. So this guy is basically RC dV out dt. Okay. So looking at this in the context of that formula that I had, so I had this as A0 V out of t plus A1 dV out dt, like that. Right? So going back to this formula, that tells me I can make this relationship as H of omega is equal to 1 over A0 plus A1 times J omega. So in this case, this becomes 1 over what? If I just try to pattern match, what do I have? One over what? What's A0? 1. What's A1? RC. So this guy becomes 1 over J omega RC. And that is exactly the same thing that I got from the impedance analysis. All right. So what I've done is I've created this sort of frequency-based relationship between the input and the output. All right. Now you know how to use that in the context of circuits, right? And we're going to try to use it in a very general context. It doesn't just apply to circuits. What I'm saying is it applies no matter what. It applies if I have something like this, this motor relationship up here, the motor's got a differential equation relationship. I don't know impedances for motors, right? But if I have a differential equation, I can use that same approach to get this thing I call more generally the transfer function, okay? Which is what I end up with here, okay? I get this transfer function relationship. This guy here is my h of omega. So what I have with that is I can say, if I want to know the phasor of the output at a given frequency, I need to figure out what the transfer function is at that frequency and figure out what the input is at that input phasor is at that frequency and just multiply them like that. So let me talk about how I would use this in terms of this picture right here. Yikes. Okay. So if I want to figure out how to solve with the transfer function, basically, again, a couple of steps, right? So what I do is I'm given this time vector, right? This input. I figure out the Fourier transform of that input. I look at the differential equation and I try to figure out the transfer function from it. Then basically what I do is I figure out the Fourier transform of the output by saying it's equal to the transfer function times the Fourier transform of the input. And then if I wanted to figure out what the actual output is, I can get what I call the inverse transform. The inverse transform would basically be to say, well, I look at what the transform is, and I know that it's going to be sine waves. So I look at the frequencies that are there, and I map them over to particular cosines. So let's look at it. Let's look at an example. An example is going to be the best way to see this. Okay. So for this guy here, I've already figured out that the transfer function here is h of omega is 1/1 plus j omega RC. All right. And I'm going to use a number here. RC is 1/2 pi 60 is what I'm going to end up with. That's the number I'm going to choose for it. Okay. So I want to follow through these steps. Right, so I want to go from my x of t, figure out its Fourier transform, then figure out the transfer function here, and then figure out what y of omega is going to look like. Okay, so, and I could use that to then figure out what's y of t going to look like. So, how do I approach that? Well, my step one is going to be basically, I got to figure out the Fourier transform of Vn of t. Okay, so how do I figure out the Fourier transform of this thing? What's the key step for me to figure that out? What frequencies are in that waveform? "60 hertz and 180 hertz, which means how many harmonics are there in this guy? There's a DC term, and there's what else? The first and the third harmonic. Okay, this guy has a first harmonic of 60 and a third harmonic of 180, 3 times 60. Okay, so if I try to get this into my basic form, I say this is 5 plus 4/2 e to the j 60 degrees times e to the j 2 pi 60 t, like that, plus 4/2 e to the negative j 60 degrees times e to the negative j 2 pi 60 t, plus, what do I do with the sine? That's a sine. How do I, first thing I got to do is get I can use that like B, the AB form of the series or whatever. But if I have sine, how does that relate to cosine?
About 90 degrees.
Yeah, this guy would basically be 6 sine or 6 cosine 2 pi 180 t minus 90 degrees, like that. So that would turn this into 6/2 e to the negative j 90 degrees times e to the j 2 pi 180 t plus 6/2 e to the j 90 degrees times e to the j 2 pi 180 t with a negative sign, negative 2 pi 180 t, like that. So for that, I can map that over to a Fourier transform by looking at the coefficients. There's going to be how many impulses in my Fourier transform based on this? How many terms are there in my Fourier transform? 1, 2, 3, 4, 5, right? 1 for each of those terms, right? He looks like, I don't know why that keeps appearing, right? It ends up, this is my V in, right? My V in of omega, I wrote it out here, right? Let me write it here. I don't want to, once you've got that waveform, you guys can see the mapping, right? So V in, this was my V in of t. This is now how I map those to each of those individual impulses. Okay. So what I then do is I have to figure out what is the transfer function. So that was the second step. What's the value of the transfer function? I don't know why it's doing that. Value of the transfer function at the frequencies I care about. So let's look at this particular example. So here's what I ended up with. Okay. I ended up with a Fourier transform that looks like this. Okay. So let's go to my MATLAB code. Okay. So what I did here in my MATLAB code, get out of the way. All right. What I did here in my MATLAB code is I basically implemented that Fourier transform as a vector. Okay, so looking at my terms here. Okay, so given this, I have 1, 2, 3, 4, 5 entries. So how many entries should be in my V in vector in MATLAB? 5, right? At what frequencies? Well, this guy has a DC term, a fundamental term, and a third harmonic. Right. So if I tell you to plot the entire Fourier transform of this thing, if I want to plot this, I'm going to end up having 7 entries, right? Why 7? Looks like it should be 5, right? 1, 2, 3, 4, 5. Why 7? The second harmonic. Yeah, the second harmonic. So the code that I have looks like this, right? This term here, this here is my negative third harmonic term, my negative second harmonic, my negative first, my DC, my first, second, and third. Okay. And then what I did, just like I did last time, I created an omega vector, right? That goes from negative 3 times omega naught to 3 times omega naught. And then what I did was I created a graph of them. Okay. So if you look at what I've done here, if I run this code, again, we did something just like this on Monday. All right, but what I've got is I use this stem command and it plots for me at the right locations what the Fourier transform coefficients look like. Right. So I have a value here at 2 pi 60, value at DC, and then I have something at 2 pi 180, which as I said is the third harmonic. Now, what I'm asking you to do in, say, problem 5 there is I'm asking you to plot, in addition to that, what that transfer function is and to plot those on top of each other. So here, what I've done is I've created a different vector. I call this omega plot, right? And I'm saying this guy goes from negative 10,000 to 10,000 in steps of 0.1. And then I created my H vector. That is the transfer function right there. So what I did here, if I go and I look at what I created. Okay. What did it do? There we go. All right. What I have here is 2 things sitting on top of each other. I've got a stem plot that shows me what my coefficients look like for the input. What's this blue thing here? There. What's that? That I plotted on top of it. That thing is the transfer function. Okay. That thing there is the transfer function for me. So I'm plotting those on top of each other like that. Okay. All right, I think you guys are gonna, I'm happy with myself for pushing the homework back till Monday. All right, we'll talk about this piece a little bit more on Monday. All right, the thing that I want to make clear to you guys before we wrap up here today is the Fourier series and being able to relate the Fourier series to a Fourier transform is going to be my primary focus for you on the exam. All right, this stuff about filtering, which we've been talking about here at the very end last time and then today, that's not something I'm going to throw onto the exam. All right, that is something you're going to need for the project, right? So what I'm trying to make you do right now is to think about that for the stuff that you're going to have to do on the project, but that is not something I'm going to throw at you on the exam. I think you will be more than ready. If you can get through the homework, you will be more than ready for figuring out the Fourier series and the Fourier transform from the Fourier series. Okay. All right. That's it.